Welcome to qnawire.
We have kind of an interesting sequence of events. Now, this is a Jane saving Tarzan type scenario. But I am modeling Jane. She is mass 1 and 60 kilograms, swinging on the end of a vine. The vine itself has a mass of 30 kilograms, and I'm making that what I call mass 2. And Tarzan is mass 3. He's on the ground to begin with, and he has a mass of 72 kilograms. But there's a sequence of events, and we're going to treat the vine as if it acts in the center of mass of the vine. So we'll treat everything like points or spheres if we really want to think about spheres. But the things to think about are the physics that goes on as Jane swings down on the vine. So up through where she's at the ground, there's basically energy conservation. That is, Jane is converting the potential energy in the vine plus herself, gravitational, turns into, so basically kinetic energy. And I am going to use not translational kinetic energy, but rotational kinetic energy at point A. And what we'll be solving for is the angular velocity of that rope vine system before Tarzan gets picked up. The second part of the sequence that we'll work through is Tarzan gets picked up in an inelastic collision. So Jane and the vine collide with Tarzan, and what we know gets conserved is momentum. And specifically, I'm going to set the angular momentum right before the collision equal to the angular momentum right after. So I'm writing down angular momentum in the form of the moment of inertia times the angular velocity. And finally, in swinging back up to a final height, and of course what we're solving for in part B is the angular velocity after the collision occurs. The last part of the sequence is where the whole kit and caboodle swings up. And I can think about that simplistically then as the new rotational kinetic energy converting back into potential energy. It's not quite that simple, as we'll see, but I can work that out as we get to that. And what we're going to be finding is the final height that the vine system reaches, and hopefully gets everybody to safety from the angry hippopotamus, the hungry hippopotamus. Yeah, it might be angry too. Okay, so let's start off with conservation of energy. And what I need is a reference point for my gravitational potential energy. And I think the simplest place to choose as reference is the ground. So we'll say ground equals 0. Anything at the ground has potential energy equal to 0. But Jane and the vine are starting up off the ground. So let's just write down the potential energies initial. And the kinetic energy is 0, so we don't have to add that. And we want to equate those to the final potential energies of Jane and the vine. Plus the K rotational 1/2 I A, we'll call it omega A squared. And we'll figure out that moment of inertia in a little bit. But the problem states that Jane starts at a height of 5 meters. And if we look at the vine, it's up a little bit higher. How much higher? I'm going to treat the vine as if it's in the middle of the vine, essentially. So there's a 3 meters left over. And so the vine is starting 1.5 meters higher than Jane, or 6.5 meters. Finally, Jane is at the ground, but the vine is halfway up the vine, or still 4 meters up above ground. Okay, so carefully taking care of those. Now, what about the moment of inertia at the initial point? Moment of inertia usually depends on the shape of the object, but here we're treating them as point masses, and the moment of inertia for a point mass is just the mass times the distance squared between the point and the support or rotational center. So for our situation, we have an mr squared for Jane. She is 8 meters from the point of support at all times. She is not climbing the rope. So we'll put Jane down as 60 kilograms times 8 squared. And we'll add to that the vine. Again, the vine will not change its center of mass from the center of the vine. Okay, and we can figure out that moment of inertia in kilograms per meter squared. And it's a fairly large value. Uh, 4,320 kilograms meter squared. Okay, now we have all the other masses, and we can simply solve for everything in the problem. I'll just show one intermediate step with the m's and the g's and the heights in there for good measure. It does help to do the algebra to have everything written in terms of numbers. And we see that the vine is just adding a little bit. And now we have our K rotational term. And I'm leaving off units, being careful to put everything in terms of meters, kilograms, and seconds. But again, we're after the initial rotational velocity of the system as Jane reaches the ground. Okay, and let's see. I don't think I need another intermediate point, but it does help to check out what I'm doing. And I'm getting omega A is approximately 1.30 rads per second. A little bit higher than that, but that should be good. Let's get the units in there. Radians per second. Okay, now colliding with Tarzan, we are going to assume conservation of angular momentum with the idea that everything is happening horizontally over a very short period of time. We are assuming no friction or hippopotami pulling on people's legs. That would be bad. So no external torques, or the external torques are small enough that we can ignore them. Probably not true if the hippopotamus is really pulling on people's legs. But angular momentum of a rigid system is defined to be a product of the moment of inertia times the angular velocity, sort of like mass times velocity for regular momentum. So we have the moment of inertia and the angular velocity right before the collision. We can figure out the moment of inertia by just working in Tarzan into the mr squared formula. And so we're after the new angular velocity. Okay, so IB at this point is going to be what we calculated before, the 4320 kilogram meter squared. But we have to add to that Tarzan's mass and radius. And we'll keep him on the end of the vine as well, just simplistically put him there. Especially if Jane is grabbing onto him. That's the point he will stay at. So yeah, a moment of inertia is a little bit larger, which means that the vine will slow down like a kid jumping on a merry-go-round. Okay, and we can put all this together. Omega B then is our initial moment of inertia, t times our initial angular speed, divided by our new moment of inertia, which is almost twice what it was before. And the unit should be radians per second. And our speed will be down by almost 1/2. Six 6.629 rads per second. Okay, so that makes sense. And of course, with a collision like that, energy gets lost in the binding of the particles, in sound, in heat needed to absorb some of the impact, I suppose. It's a good way of putting it. Alrighty. So now, swinging back up, we are going to conserve energy again. Okay, so Jane and Tarzan are on the ground, but the vine has potential energy of m2 times g times 4 meters again. There is now rotational kinetic energy of a different amount a smaller amount than before the collision. If we're finding how high everything rises, the final kinetic energy is 0, so we don't have to worry about that. But we do have to carefully think through the heights. Of course, Tarzan and Jane, we'll call them M1 plus M3, will have a new gravitational potential defined by that final height we're trying to solve from. The vine starting off at 4 meters will be 4 meters still above the ground, plus, let's see, let me come up with a good picture for the final height of the of the vine. I'm not sure I have that in a good way. I have 4 meters plus the final height over 2. Let me make sure that that makes some sense. Okay, so I'll just draw a picture to kind of convince myself that that's true. So it started off half the length, 4 meters. And yes, it will rise by half as much as Tarzan and Jane because it is halfway up the vine. A better picture here. Yeah, similar triangles will do it. Okay, let's see. I don't like my picture. I think there's got to be a better way to draw this. Or a better way to look at it would be from our initial situation. This will be just kind of the same situation in reverse. So in the initial situation, the Jane fell by 5 meters and the vine fell by half of that, 2.5 meters. So yes, if Jane rises by h, the vine should rise by h over 2. I think that's a better way to look at it. Okay, and we can kind of just check from side to side that the vine goes up by half the distance that Jane does. That's probably better drawing, but trying to draw similar triangles, they look kind of messy. Okay, so now we can solve for the final angular velocity of the vine. Let's see. IB is going to be IA plus the mass of Tarzan times his radius squared. And so that's going to be quite large. We've already figured it out, have we? Yes. 8928. Okay, and let's see. Let's figure out some pieces. I'll put 1/2 IB omega B squared all together. And I'll put all the energy stuff on the other side. Let me see. So we've got M1 plus M3, 132. And then we've got M2 1/2 times G times HF. And here I've gone ahead and canceled the 4 meters that the M2 vine starts with. And when I figure that out, the final height is really quite depressing. It's about 1/4 of what it started out to be. So let's hope it is high enough to get away from that hippo. Hippos probably can't stand on their hind legs, so this might be safe. Maybe.